All right, welcome to The Explainer. Today, we're diving into an idea that was, well, it was more than just revolutionary. It didn't just solve a few problems, it literally connected two completely separate worlds of thought, and in doing so, changed mathematics forever. So let's jump right in.
So, for centuries, you got to picture mathematics living in these two completely different worlds, right? On one side, you've got geometry. That's the visual stuff, the intuitive world of shapes, lines, and angles. Things you can actually see. And then, way over on the other side, you've got algebra. That's the abstract, logical world of symbols, x's and y's, and all those equations.
Now, both of these languages, they were super powerful in their own right. I mean, you could do amazing things with them. But here's the thing. They couldn't talk to each other. It was like they were speaking completely different dialects. And that was the reality for a long, long time, until one just brilliant idea came along and built a bridge between them.
And that idea, it's called analytic geometry. You've probably heard it called Cartesian geometry too, and yeah, that's a big clue about who was involved. So what is it, really? Well, at its core, it's this incredible method for describing shapes using numbers and equations. And just as important, it lets you pull numerical info right out of those shapes. It's a two-way street.
And the tool that makes this whole thing work? Well, it's almost ridiculously simple. It's the Cartesian coordinate system. Yep, it's just a grid. But don't let that fool you. Its genius is that it gives every single point in space its own unique address, a little pair of numbers, its x, y coordinates. This simple grid, this is the foundation of that whole bridge we were talking about.
So, what analytic geometry really does in a nutshell is it transposes information. That's a cool word, right? It literally means to place across. And that's exactly what's happening. We're taking a shape from the visual world of geometry, and we're placing it across that bridge into the world of algebra. We're translating it, turning pictures into pure logic.
Okay, so that all sounds cool in theory, but how does it actually work? Like, what are the rules for this new language? Let's open up the dictionary, so to speak, and see how we translate some basic geometric ideas into algebra.
Let's start with the simplest thing, a point. In this new system, a point isn't just a dot anymore. Nope. It's now an ordered pair of numbers, its coordinates, that give you its exact location. The x tells you how far to go left or right, and the y tells you how far to go up or down. A physical spot just became pure data.
All right, how about a line? A perfectly straight line, something you draw with a ruler, can be captured perfectly by this one little equation, y equals mx plus b. The m there, that's the slope, basically how steep it is, and the b, that just tells you where the line hits the vertical axis. Think about that, an entire infinitely long line, boiled down to just a few symbols.
And this is where it gets really beautiful. A perfect circle. It's only defined by one thing, right? Its radius. And it gets this stunningly simple equation. This formula here connects the x and y of every single point along the edge of that circle. It's so elegant, so precise, it's just perfect. And it doesn't stop with simple stuff like lines and circles. Oh no, you can take way more complex curves. Think ellipses, parabolas, hyperbolas like you see here, and they all get their own unique algebraic equations. The big takeaway is that basically any shape you can imagine can be translated into the language of algebra.
Okay, so we can turn shapes into equations. Big deal, right? Well, yeah, it is a huge deal. Why does it matter so much? Because once that shape is living in the world of algebra, we can unleash this whole arsenal of algebraic tools on it. We can analyze it and mess with it in ways that were just impossible before.
So what kind of problems are we talking about? What can you actually do with this new superpower that you couldn't do before?
Well, for one, we can find the exact distance between any 2 points. I mean, before, what would you do? Grab a ruler and hope for the best? Now, all you need are their coordinates and this simple formula. And here's the cool part. If you look at that formula, it's really just the Pythagorean theorem, a classic rule from geometry, just wearing an algebraic costume.
Or how about finding exactly where two shapes cross each other? Like, where does a line hit a circle? Instead of trying to draw it super carefully and just kind of guessing, we can now take the equation for the line, the equation for the circle, and solve them together. The answer you get isn't an about here. It's the exact coordinate point where they meet. No guesswork needed.
And maybe the coolest part, we can play God with shapes. Seriously. By just changing a little number in the equation, add a 5 here, divide by 2 there, we can move the shape, stretch it out, flip it upside down. We basically become digital sculptors, and algebra is our chisel.
Now, an idea this big doesn't just pop out of nowhere. This bridge, it took centuries to build. So let's take a quick look back at the history and meet the key architects who made it all happen.
The story really starts way back with the ancient Greeks. A guy named Apollonius of Perga got really close. Then, fast forward to the 11th century, and the Persian genius Omar Khayyam, he saw the deep connection and did a ton of work to close the gap. But the final breakthrough, the moment it all clicked, came in the 1600s with two French mathematicians, René Descartes and Pierre de Fermat. Working separately, they both cracked the code.
So what was the big deal? What did they figure out that was so different? It was all about a huge shift in thinking. See, for the Greeks, you'd start with a shape, a curve, and then try to find an equation to describe it. Geometry was the boss. But Descartes and Fermat flipped that completely on its head. They said, wait a minute, what if we start with the equation and see what curve it creates? And that was the revolution.
And believe me, the impact of this idea doesn't just stop at a flat, two-dimensional piece of paper. Not even close. The same exact principles can be launched into whole new dimensions.
All you have to do is add one more coordinate, a z, for depth. And just like that, you can map out and control things in three-dimensional space. Every single point in the room you're in right now can get an x, y, z address. And that means we can suddenly write the equation for a sphere, or a flat plane, or pretty much any crazy 3D surface you can think of.
And this is not just some dusty old math concept. This is the language that runs our modern world. I mean, it's absolutely essential for plotting a course to Mars, for designing a new jet engine, and you better believe it's the bedrock of all computer graphics. Every incredible special effect you see in a movie, every realistic world you explore in a video game, all of it is built from the ground up on the principles of analytic geometry. So when you look back, the story of analytic geometry is this incredible lesson, right? It shows that sometimes the biggest leaps forward don't happen inside one single field. They happen when someone builds a bridge between two fields that everyone thought were totally separate. Connecting different ways of thinking can spark an explosion of new ideas. And that kind of leaves you wondering, doesn't it? What other languages out there, in science, in art, wherever, are just waiting for someone to come along and build a bridge?